Hi everyone, so today I'll be explaining my final submission that I did in this Recod.ai competition. So you can see in the public leaderboard evaluation I have been ranked 665, which is not that good, but I just gave 1 week of time to the competition, and with that if I'm able to achieve 665, and I guess there are 15 to 5 participants, which is a little bit more than like lesser than 50%. So in top 50 percentile I'm in. Cool. So but yeah, still this is the leaderboard metric. So private leaderboard metric will be coming out I guess after 3 months. But yeah, so in this video I'll be explaining what all things I have tried, and how I achieved this 0.312 score. Cool. So dedicated to this video I have created this GitHub repository, which if you want you can go through it. So here I have explained all my complete inference, pre-processing, post-processing, which model I like went for, and yeah, all that thing I have explained it here. So yeah, let's go step by step. Cool. So in this competition, the challenge was, so wherever there are so like yeah, just to keep the premise, so the competition was to detect scientific image forgeries. Okay, so this was the competition where we have to detect whether there is any instances of copy move forgeries exist in the image. If none exist, uh, classify the image as authentic. But if you are observing some copy move forgeries, uh, you just don't label them with like forge detected. You also need to give out the region where you are seeing the copy move forgeries has occurred. So yeah, so due to this they have kept this evaluation metric as a variant of F1 score, where your authenticity gets calculated, you can say, by accuracy, and but the region that you are proposing, uh, where the copy move forgery has occurred, is computed using a F1 score metric. So yeah, that's how this evaluation metric is set. Now so yeah, that was a challenge, and yeah, the F1 score was calculated using a RLE encoded basis, where wherever you are very confident the pixels are forgery, you just give out the pixel values, and yeah, that's how you encode your probability maps into a string. So that's RLE encode for you. Cool. Then so yeah, in my previous video I have shown you like how I trained the model, and I showed you a couple of results that I'm giving like that I'm getting out of the model. But the main thing that I observed, so when I did the submission to that, okay, if you look at my initial scores, those were pretty bad. Okay, so you can see like I was not at all achieving like not at all, you can say, like these submissions. Okay, I'm not at all achieving like point 0.1. Okay, so why did this occur? So what I observed is, so see, the your F1 score was heavily amputated by how well you are detecting authenticity, because um, so for a given image, okay, if you are seeing like none copy move forgeries, then you have to classify that as authentic. Okay, but if you are detecting it as a forged image, okay, forged image, then you have to segment it. Okay, you have to segment the portion. Okay, now this is based on your RLE based F1 score calculation. Okay, but here it's simply a accuracy. Okay, so you can think of, so if you simply say all of the images are authentic, okay, so whichever images are actually authentic, they will indeed bump up your score. Okay, so in my case what was happening is my model was very high recall. Okay, so my model has a very high recall. What does that mean is, even for authentic images, okay, it was predicting masks. Okay, due to which I was not at all like classifying any image as authentic. Okay, so what I need to do is, what I did is I created some gates. Okay, in order to post process my mask and in order to classify authenticity. Okay, so yeah, um, cool. So what I did is shown here. Okay, so first of all, in my pipeline, when I receive the input image, I load it as a RGB image. Okay, now I'll come to this YOLO detection. Okay, but yeah, for every image, okay, I was basically running the segmentation. Okay, then whatever probability map I was getting, okay, I was performing some threshold based authenticity classification. Okay, so I did three gates for my classification, like segmentation. Okay, the first one was connected component based, component net based. Okay, the second one was a mean area threshold. Okay, and the third one was simply area threshold. The third one is basically a area threshold. So yeah, what was happening was, so basically for a given image, okay, um, I was detecting, like I was segmenting some region which where I am finding copy move forgeries. Okay, but yeah, there were also some salt and pepper kind of masks also the model was giving out. Okay, now the main thing is the model was giving out a probability map. Okay, where at every pixel the model was giving a probability score. Okay, so for this pixel it was giving a probability score of how confident it is, like the pixel is a forged or not. Okay, so in order to convert it into a binary mask, okay, uh, to a binary mask which is this, where I will only have white and black pixels. Okay, I need to apply some kind of a thresholding to here, right? Or I can write it something like this, right? Now the main problem I was having is, so per image threshold I was getting different threshold. For like for this image I was getting some T1 threshold, for another image I was getting some T2 threshold. So what I did is I did a adaptive thresholding, which is pretty similar to, if you guys are like aware of Otsu thresholding. Okay, so you guys can read about it, but what I was doing is, see, if you think of the forgery task, it's basically detecting the boundaries of the forged regions, right? Now whenever we are in a image, okay, whenever two objects, like for me also, this is my hand. Okay, you can think of like my face as a background here. Okay, when my hand enters into my face region, okay, the pixel values that you are guys seeing for my face, okay, those get altered. Okay, so you can think of something like the change of pixel values. Okay, when my hand is entering to my face, okay, the gradients of these pixel values will be much higher as compared to the other regions in my face, right? Because something else is entering here. Okay, so what I did was, so once I get this probability map, okay, so I calculated the gradients of all the probability score with respect to x and y axes. Okay, you can say um, do pixel with respect to x, then do pixel with respect to yo y. Okay, cool. So I was getting these two. Now what this will give me is, this will easily give me wherever in my probability map there are edges. Okay, now in order to convert into a binary mask, okay, I was keeping a threshold of so then I was like mixing them up, okay, generating a complete gradient map. Okay, so this technique is pretty similar to how we perform thresholding in O2 thresholding, or you can think of Sobel based thresholding. Okay, we basically compute the gradients of the pixel value changes, and what this will give me, this will give us edges. Okay, so this technique is pretty similar to that. So I just applied it on my probability map. Now once I have this gradient map, okay, then I can apply some threshold, something like, so I was doing mean of this gradient plus uh, zero 0.3 of the standard deviation of this gradient map. Okay, now this threshold is adaptive. How? Because this threshold is being computed per image. Okay, I'm not hard coding any threshold value, so I'm just giving out the probability map for every image. Okay, calculating the gradients. Okay, then creating the gradient map, and then performing this and then calculating this mean and the standard deviation and getting this pixel value. Then I can apply this same thing. Okay, once I got the threshold value, I'll just simply apply it over this gradient map and convert this uh, probability map into a binary mask. So this was my idea, to create this binary map. Okay, so you can see you can like say this was how to generate binary mask. Okay, now even with this, since my model was very forgery biased, so any image you will give, okay, it will just say like, hey, forge region, forge region, forge region. Now I need to reduce down the false positive. Okay, so by reducing false positives, okay, that will basically bump up my authenticity prediction, right? So for example, let's say if I perform some gating, okay, and let's say in the uh, binary mask I have something like this mask, these kind of mask. Okay, now if this image is actually an authentic image, okay, then the probability values for these regions, okay, those will be pretty like the model will be less confident. Okay, so I can rule them out. Okay, using some techniques. Okay, so what I did here is, so I used, so yeah, after attaining this binary mask, okay, I was doing a step 2 of performing uh, dilation. Okay, and or you can say morphological closing and opening. Okay, so what does this mean is, so it's a CV2 functions. Okay, it basically runs a kernel. Okay, so closing means you close out the gaps between your mask. Okay, so if I show you an example, so this is taken from the CV2 documentation itself. Okay, so if you see opening, okay, or let me first show you this closing. Okay, let's say my segmentation is something like this, just like this J. Okay, it has predicted all these regions. Okay, but you can see inside that region I still have some black spots where the model is saying, okay, I'm not confident whether this is force region or not. Okay, so in order to like convert them into force regions, okay, I will apply this like I was applying this morphology closing kernel over this predicate like binary mask and converting into something like this. Okay, so by this I'll be bumping up, or you can say fine tuning my forced prediction. Okay, then in order to remove those salt and pepper noises, okay, I was then after closing I was performing this opening. Okay, where for this kind of small segmentation detection, when I run this opening kernel, okay, it will simply nullify this small region. Okay, now why this is necessary? Since I need to reduce down the number of false positives, okay, because my model was pretty recall heavy. Okay, I need to get rid of this, because by going this, these kind of predictions, okay, these kind of prediction can be easily classified into authentic. Okay, so yeah, I was performing this morphology close and opening, and with that I was getting my fine-tuned binary mask. Okay, cool. So yeah, after this I was getting my fine-tuned binary mask. Okay, now the my next task was to uh, do some gating logics. Okay, so the first gate logic that I did is a related to like connected component thresholding. Okay, so what this basically does is, so what I did is, okay, so during my validation stage, okay, I created this binary mask for all my validation data. Okay, now within my validation data, whichever regions was my actual force regions, okay, I calculated like I overlay both of them. Okay, for example, um, let's say my model has predicted like in this image this is a force region, this is a force region, this is a force region, okay, like this. Okay, but the actual ground truth lies something like this. Okay, let's say this is GT, this is spread. Okay, and this was this I was doing during my to my validation data. So validation data, and that to be forced. Okay, now here what I was doing is, so um, yeah, now so you can see my model is predicting like 4 masks here. Okay, but in the actual ground truth there is only 2 masks. Okay, um, so in order to nullify like this mask, okay, let's get a new color. In order to nullify, let's say this mask, okay, uh, this mask and this mask, okay, and only select this mask. Okay, I was performing this CC thresholding, and what it was doing was, so it was calculating how many pixels, okay, I should consider to be there in my mask. Okay, so I run through a pretty like a big grid search in order to achieve that. So if I show you the code, scripts, where's this one? Yeah, so yeah, when I applied this grid search, okay, I was basically doing multiple pixel like area, like number of pixels as thresholds. Okay, and I was giving it to this remove small component function. Okay, and this is being run on my validation data. Okay, so with respect to this I got a number. Okay, which was giving me how much pixel should I consider so that the forgery should be like the segmented region should be treated as a forge. Okay, so this was giving me number of pixel to be there in a forgery. In a segment portion. Okay, so with that you can think of, I was nullifying this guy. Okay, but I was still having this too. Okay, then another thresholding I did is the mean area confidence threshold. Okay, so what this threshold was doing is, so let's say, so when I overlap this image, like the right image to the left image, okay, then I will see a overlap something like this, right, where this left image, like the predicted image center patch, okay, it will overlap with the ground truth. Okay, now this overlap, okay, I can see the confidence value of my model in this region. Okay, so the confidence value, uh, you can say the in this patch the confidence value of my model in this region, if I take the mean of them, okay, and I do it across all the image, okay, and then then take the mean, okay, so I will arrive at a threshold in which I can nullify the mask even more, okay, so that will basically tell me how much confidence or the area overlapping I am having, okay, with respect to the correct mask and my model predicted mask, okay. So yeah, with that you can think of I was nullifying these two, okay, because what will happen is uh, this region will have a very high probability mask, okay, these region will not have very high probability, okay, and those will get automatically nullified by my mean area confidence threshold. So yeah, along with this, even with CC thresholding, I also kept an area metric, area threshold, okay, because from this overlapping I was getting some amount of area that I should trust, okay, so that area threshold as well as this mean confidence thresholding I was keeping, so that I will know how much confident pixel values I can trust, okay, so that I can rule out these ones, okay. It like there are still some cases where the model was still not correctly predicting, okay, but yeah, the bump in my validation set I got from this threshold. So yeah, you can say area of model confidence threshold and high confident region threshold. Yeah, cool. So yeah, now after this, if a segment portion was like, let's say even after all this, okay, if I'm still getting some mask, okay, then I was classifying it as a force region, okay, as a forced image, and I was converting into a RLE encoded string for my submission, okay. But let's say after all this threshold, it outputted me uh, null binary mask, okay, where every pixel is black. That basically means I didn't find any mask, okay. So that then I was labeling it this image as authentic. Cool. So this was all the post processing that I did uh, for a mask, okay. Now so even with this, okay, all this processing, I was still into like this 0.3 0.24, so my score was between 0.3 to like 25 to 34, okay. So I just gave a thought like what was happening, okay. So with all this, my leaderboard score was like keeping between 0.25 to 3, okay. Then I read the problem overview, okay, then I observed this supplement images, okay. So these are the images which are pretty different from the images they have given us for training, okay, and these images are pretty close to the test, okay. Now if I show you the supplement images, supplement, yep, okay. So these are the supplement images, okay. Now here you can see, okay, in this image there are multiple images attached, or you can say multiple panels attached, okay. So this is the image, this is the image, let me see if I'm recording. Yep, yeah. So this is the image, this is the image, okay. So there are multiple panel of images, and if you look at the train images, they were something like this. Okay, these are not multi-panel. Okay, they are actually the cropped regions, okay, from the supplement images. Okay, now this is a pretty domain shift of the data on which my model is trained, okay, and the data that was given during test. Okay, so both are completely different, right? So yeah, what to do? So in my final day, okay, I was thinking like how to bump up my score. Okay, so I was thinking like how to do this multi-panel image detection. Okay, one way. So during my earlier submission, I was simply giving out the whole image. Okay, now this whole image uh, will, so this is also a pretty big image. Okay, you can see like these are some 2K and 4K images. Okay, so this pretty big image, when you are compressing it to get it down to your model dimension or model input dimension, you will be losing out pretty much like you will be losing out pretty good quality of features, okay, or actual the force information, okay, because when you are reducing this this 1200 by 700 images, okay, to a let's say 500 by 500 image, okay, most of the pixel values will be dominated by this white region, which we don't care, we only care about the panel. Now this panel images will also get reduced. Okay, so in order to tackle this, what I did, I broke this problem into a detection plus segmentation problem. Okay, so in my last day, I just had this idea, why don't I detect this panel itself. Okay, so given this image, okay, once I have the panels being detected by let's say some method, okay, then I can crop out that panel region, okay, and then send that panel image to my model, okay, because that is the data on which my model is trained. Okay, so I just quickly go through and install like go through Ultralytics, and I installed YOLO. Okay, so if I show you my training, I just trained a YOLO model for this. Yeah, sure, anyway. Okay, and voila. And yeah, before doing that, so what I did is, so I had this train images. Okay, in order to train my model, like train my YOLO model or this detection or detection model, I need some data. So what I did is, I just took different combination of the trained images, okay, and I pasted it into a pretty big whiteboard. Okay, so I created this kind of synthetic data, okay, which is pretty similar to how the supplement data is being given. Okay, and this is the data on which I trained the YOLO. Okay, also in this data I tried performing like training my segmentation model. Okay, but it didn't perform well. Okay, it went to point to leaderboard score. Okay, I think that was mostly happening because of this white regions. Okay, they are acting as noise. Okay, because due to this white region there is a very sharp gradient across the border of the images. Okay, and that can be confusing for the model. Okay, so yeah, so I created this data set, I trained my YOLO. Okay, and with that I was collecting the panel lesions, you can see like this. Okay, now with YOLO also you can see it was detecting these kind of regions. Okay, I also did some thresholding on that part also. So if majority of the pixel values are white, okay, discard that portion. Okay, so all this kind of thresholding. Okay, so yeah, this code is available in my GitHub, so you can go through it. Yep, code. Yeah. So yeah, this code is available here, so you can download it. It's pretty big for GitHub to show, but yeah, this is how the notebook looks. Okay, so yeah, so there were certain threshold on the confidence value also, as well as the overall pixel region. So yeah, now my inference pipeline looks something like this. Okay, so these are all my post processing. But yeah, given an input image, okay, I was running my YOLO model, okay, to detect the panels. Okay, so where should my segmentation model should look? Okay, now each panel was being detected by my model, or you can say by my segmentation model. Okay, and then it was going into this kind of post processing. Okay, and yeah, once this mask has been predicted for that region, okay, I was simply creating a grid with the similar dimension as my input image. Okay, same dimension. Okay, and I was pasting the mask over that. Okay, so yeah, this was my overall pipeline in my submission, and yeah, with that I got some bump ups in my last day submission. So from 3.1, okay, you can see these. Okay, yeah, I got my final score to 0.312. Okay, and that landed me up in this 665 rank. So yeah, this was my overall pipeline and my submission idea. So I can also show you this. I've also added this submission notebook in my GitHub, and code wise, if I show you, you can see like these are the threshold values for my respective models. For me, I went to a hybrid model of DINOv2 and PSP and FPN model. So I'll show you how the model works. But yeah, I tried a unit model and this pyramid style model. Okay, the pyramid style model was working better for me. So yeah, and these are the respective parameters for that. Then yeah, and yeah, one more pre-processing I applied on the image was this Clahe enhancement. So there were many histology images where there are cell images, okay, and those were pretty darkened up. Okay, so in order to increase the brightness, okay, so that regions can be displayable, I applied this Clahe. Okay, then yeah, this was the code to generate the binary mask, okay, from the probability map. Okay, so yeah, you can see I was calculating the gradients. Okay, then I was calculating the gradient norm, and based upon that I was computing the threshold. Okay, then yeah, then I was doing this mask closing and mask morphology closing and opening, and I was giving out the mask as well as the threshold. So yeah, then yeah, this remove small component is for the connected component based thresholding, okay, to rule out the mask regions. Then yep, all this. So yeah, this is my main inference code. So I was loading my detection model, okay, loading the weights, then I was loading my segmentation model. Okay, then yeah, then I was just going just a second. Yeah, so I was going through each images, and yeah, then I was getting the panels from my detection model. Okay, then yeah, so then there was this thing. So not all test images in the private test set, okay, are synthetic style images. The author has also said that there will be a mixture of the train images as well as synthetic images. Okay, now for my YOLO model, what I observed is whenever there is no box detection or there is a single box detection, okay, then it was a image with respect to the actual train image. Okay, so it was a image of this kind. Okay, so for these kind of model, my YOLO was predicting a single box. Okay, but yeah, for synthetic images, it was predicting multiple box. So yeah, I just did this logic that whenever the number of boxes prediction is not there, or there is only one prediction, okay, send the whole image to the model. Okay, and also apply some cropping there. I did a 20 pixel margins. So yeah, and for each panel image, okay, run the segmentation model, okay, and get the mask prediction. Okay, then yeah, these are the gating logics. So removing the small components using connected components. Then there is this mean area inside. Okay, so per region it was calculating the confidence value of the model from the probability map. Okay, then yeah, I was just thresholding it with respect to my validation data based threshold. Okay, then yeah, and then after all these checks, okay, if I'm still getting some mask, okay, then I was predicting it as a forced, and I was annotating with the RLE encoded basis of the forced region. Now in the other case, if there are no masks, okay, I was simply giving out as authentic. Cool. Then yeah, after this I was simply just to check my prediction, I was doing this. Okay, uh, you can see like if the submission mode is not on. Okay, so for a couple of images I was trying out how the model is performing, so you can see something like this. Okay, so yeah, this was the ground truth. Okay, and yeah, this is how the model was performing. And if I show you a couple of results in my local, so mhm. Mhm. So yeah, as you can see, this was how my segmentation model was performing. So you can see it's pretty recall heavy. So even for a authentic image, okay, there is no mask, it was still predicting these kind of images, like these kind of segmentation mask. Okay, but yeah, after the thresholds, okay, I was getting good matches, okay, in authentics. But yeah, still in some region it was still giving out some mask. My thresholding was not at all working here in these cases. But yeah, so wherever there were like salt and pepper kind of segmentation mask, it is performing really good. Then for forged images I can show you a couple of examples. Let's go with this. Okay, this was authentic. Yeah, this is as forged. Now you can see this is how my model is predicting. So the actual ground truths here, and yeah, my model predicted them as well as it gave some false positive. Okay, now to rule out these kind of masks, okay, I was applying those gates. So yeah, you can see a couple of predictions. Yep, he was able to catch. Nice. Cool. But yeah, there are still some noises here. Cool. So far it was a pretty good competition. I learned many new things. Okay, and I guess the top solutions are trying some shift, like shift and some they were like defining the problem in a different domain, not in a image domain. They were doing some discrete cosine transformation of the image, and then they were doing something. So I haven't went through that path because I only had 1 week, so I just tried different ways to uh, stand out in the leaderboard. But yeah, so yeah, I guess the last part will be the model discussion. So what I did, so you can go through this repository. So in the readme, yeah, now if I go through the complete pipeline, so yeah, once I get the RGB image, I was getting the YOLO prediction. Then with respect to the number of boxes, there are two. If there is only less than one box, okay, segment the full image. If there are more than one box, crop each image. Then apply the Clay enhancement and some test time augmentation also. So vertically flipping and horizontally flipping the image, and then giving the model to give the probability map. And yeah, once you get the probability map, I was applying this connected component threshold and this mean area thresholding. So yeah, now after all that threshold, if they are passing the thresholds, after all that thresholding, if I am still getting some mask, okay, then I was predicting, then I was really encoding the binary mask. Otherwise I was simply saying this is the authentic image. So yeah, this is how I create the submission file. So yeah, so all the hyperparameters that I have used, I have added in the documentation, and yeah, these are the pre-processing of this adaptive probability thresholding, morphological maps. Now yeah, this is my model, so how I trained. So yeah, so in this competition, so if I show you, so the top model was DINOv2. Okay, so it was performing really good in the competition. So if I show you the model section, so yeah, many people are using this DINOv2 base. Okay, I didn't try with the larger version. Okay, I didn't have time. Okay, I just need to build something, but I could have gone through this large model also. But yeah, I use the base model, okay, as a foundational model. Now, then what I was doing was I was collecting the attention maps from different transformer blocks. Okay, now in each attention maps you can see the layers that I have used. Okay, I was applying this pyramid pooling, where just like a pyramid wise, I was performing pooling operations. Okay, and then for every pooling feature, I was applying this FPN. Okay, then what this FPN does is, from the pooling, it apply convolutions. Okay, and it generate these fused features kind of form. Okay, you can see like from each attention map this pooling is working, and for so now this block is happening for all the attention maps. Okay, in the image I just showed for one of them as example, but yeah, per attention map this PSP and FPN layer were working, and they were generating this segmentation mask. So yeah, now here the trainable parameters were this UPerNet, this decoder layer. I was keeping this backbone freeze. Okay, I was not fine-tuning DINOv2 weights, because the data set was balanced between authentic and forced. Okay, so no five-fold training needed to be done. Okay, I simply went through a simple train test split, or a out of fold distribution, out of fold training. But yeah, so the number of data points were not that much, uh, like, which can help me to even fine tune DINOv2. So I just freeze out the whole backbone. So yeah, I used DINOv2 base. I could have gone for DINOv2 large, and maybe that could have given me a better result. So yeah, with this I got this 0.312 score, and that landed me up in 665 rank in the public leaderboard. So yeah, this was my approach, and these are all the things that I did for my submission. So yeah, I learned many new things. So yeah, it was an interesting competition. I want to check how the people are getting beyond 0.4 score. So had to yet check, okay, how this guy is like getting 0.458. Okay, so I have no idea what this guy has done, but yeah, cool. So fingers crossed, 3 months to go. So my model will be running over their private data set, but yeah, need to go. Cool. So if you like this video, please do put a like, okay, and you can subscribe to the channel. So I'll be posting more Kaggle videos, okay, and my submission and my training approaches during the competition. So if you guys want to learn how to do a POC on the competition, okay, how to submit, okay, or how to choose model, or what to do with the data set, okay, and how to train, okay, all that thing will be covered in my videos. So yeah, just stay tuned to watch more videos on this channel, and with that, bye bye, thank you for watching.